Yes, welcome. So today we will be moving to the next topic, which is arithmetic operation. So till last class we have discussed about these subroutines. Okay. So now we'll be moving to the next topic, which is arithmetic operation. So basically here we'll be discussing about uh, the arithmetic algorithms for multiplication and division of for binary and BCD numbers. Okay. Fine. Let me start. So we'll be understanding like how multiplication is performed in a computer, right? Because multiplication is one of the major activity uh, which will which will happen normally, right? Okay. So before starting, let us try to understand how binary numbers are multiplied manually. Right? So here you can see there are two binary numbers. One is 13 represented in binary using 8421 code. You can easily understand 8421. So this is 8 position there is a 1, 4 position there is a 1, in 2 position there is 0, and in 1 position there is 1. So wherever there is a 1 position, add that. So it is 8 plus 4 12, 12 plus 1 13. Okay. Similarly this is 1 in 8 position, 1 in second position, and 1 in first position, that is 8 plus 2 plus 1, that is 10 plus 1 11. So these are the two numbers which we want to multiply. So in case of normal manual multiplication, which you know already, which is that elementary school multiplication, so this 1 is multiplied with this. Okay. So you get the same thing as it is. So 1101, right? So like that, again 1, and you get the same thing. When it is 0, here it is all zeros. Okay. And again it is 1, so this is all, it is 1101 to whatever the multiplicand. Okay. So this is multiplicand and this is the multiplier. We refer multiplicand as m and multiplier as q. Okay. So wherever m comes, it represents multiplicand, and wherever q comes, it represents multiplier, right? Finally add all these things. So this is 1, this is 0 plus 1 1, this is 1 plus 0 1, this is 1 plus 1, 1 plus 1 is what? Binary, in binary addition, 1 plus 1 is equal to 1 plus 1 is equal to actually 1 0. The sum is 0, carry is 1, whereas this here 1 0 in the sense the sum is 0, and there is a carry 1. Okay. So 1 plus, so 1 plus 1 is actually 1 0, right? Again 1 0 plus 1 is 1 1. Again 1 0 plus 1 is 1 1. So it means sum is 1 and carry is 1. So when you add 3 ones, actually you get sum as 1 and also carry as 1. So here there is a carry 1. So again 1 plus 1, it is 1 0. So the sum is 0. Again there is a carry 1. Again 1 plus 1, it is 1 0. Sum is 0. Carry is 1. Again 1 plus 1, it is 1 0. Sum is 0. Carry is 1. Okay. So finally you got this value, right? So you got this value. This is a binary value. You can convert it to decimal. When you convert it to decimal, it is 143. Okay. This is what? This is 2 to the power 0. This is 2 to the power 1. Okay. This is 2 to the power 2. This is 2 to the power 3. Okay. 2 to the power 4, 5, 6 and 7, right? So you just add all these things. What is 2 to the power 7? What is 2 to the, so 1 minute. So 2 to the power 7 will be 2 to the power 0 is 1, right? 2 to the power 1 is 2. 2 to the power 2 is 4. 2 to the power 3 is 8. Okay. And 2 to the power 7 is 128. Okay. So 128 plus 8 is 136. 136 plus 4, 140. 140 plus 2, 142. 142 plus 1 is 143. So which is the decimal equivalent of this number, right? Okay. So when you multiply two numbers of n bits, the product will have 2n bits. Okay, this is a thumb rule. Okay, when you multiply two numbers where each of n bits, the product will have 2n bits. Okay, here we have multiplied two numbers each of 4 bits, and the product contains actually how many bits? You can see here 8 bits. Okay, 1 2 3 4 5 6 7 8, right? Okay, so from this what we can, so this is basically human way of elementary multiplication, but from this what knowledge we can understand, what knowledge we can grasp, in the sense multiplication is nothing but a repeated addition. Multiplication can be viewed as a repeated addition of shifted version of the multiplicand. Okay, it is nothing but the repeated addition of shifted version of the multiplicand. Okay, so if you see here, this is 1101, this is same as the multiplicand. So first time we kept 1101 as it is. Okay, right? In the second time it is shifted to the left by 1. Okay, right? In the third time, so that is based on the input, that is based on the multiplier. In the multiplier, when the most significant bit is 1, in the multiplier, here you can see in the multiplier the least significant bit. Okay, this is the bit 0 of the multiplier. This is bit 1, this is bit 2, and this is bit 3. When the bit 0 is 1, if the bit 0 is 1, okay, then what you do, you don't shift. Okay, whatever the bit number, that much times it should be shifted. If the bit 0, for bit 0 you do 0 shifting. Okay, you do 0 shifting. If it is 1, then just copy the multiplicand. If it is 0, just fill up with 0 here. Okay, and the first bit, when the first bit is 1, if the first bit is 1, then copy the multiplicand and shift it by 1 time. Okay, this is left shifted by 1 time. Okay, this is left shifted by once, right? If the first bit is 0, then also left shift by 1 times. Okay, but copy zeros, not the multiplicand. Okay, and if the second bit is 1, then copy the multiplicand and shift it by 2 times. But here the second bit is 0, so don't copy the multiplicand, but shift it by 2 times and fill up with zeros. Okay, if the third bit is 1, then copy the multiplicand and shift it by 3 times. Okay, so the thumb rule is, if the ith bit is 0, then copy the if the ith bit is 0, then fill up with zeros and shift it by 0 times. That's it. Okay, if the ith bit is 1, then fill up it with multiplicand and left shift it by I times. Okay, so this is the thumb rule, and then add all these things, and you will get the product. Okay, so actually we are trying to understand, like, how can we make a computer to multiply. So this is so you can write an algorithm like that to make a computer to multiply. That is, given a multiplicand and given the multiplier, from the rightmost bit, I mean from the least significant bit, read the least significant bit, the 0th bit. Okay, I mean read the ith bit, or the algorithm in the sense, read the ith bit. If the ith bit is 0, then just copy zeros and shift it by 0 times. Okay, if the ith bit is 1, then copy the multiplicand and shift it by I times. Okay, like that do for all the particular digits in the multiplier. Okay, depending on the length of the multiplier, you do that many times. Okay, finally whatever the things you got, add everything. Okay, add everything, and that will be the sum. Okay, so this is the basic understanding, like how can we implement this in the computer. Okay, so our basic understanding is multiplication is nothing but a repeated addition by shifting the multiplicand. Okay, repeated additions by shifting the multiplicand. And another thing what you can observe is instead of adding all together at the end, we could also add the partial product at each stage. Okay, for as a human perspective, we feel convenient like adding all together, all the four things together at the end. But for a computer, for but when you write an algorithm, this may not be convenient. Okay, you can first perform this addition, like cumulative addition, then you can perform this addition, then you can perform this addition. Okay, if you want to find the sum of n natural numbers, if you want to write sum of first n numbers, how will you write the algorithm? First you will set sum is equal to 0. Okay, then you will say s is equal to, maybe you will write a for loop. Okay, for I is equal to something, for I is equal to 1 to n. Okay, for I is equal to 1 to n, what we do, we do s is equal to s plus I. Okay, we say that s is equal to s plus I, right? So that's what we do. We are not adding all together at one time, rather we are doing a cumulative addition, because that is actually comfortable in when you are when it is done by the machine. Okay, or a computer. Okay, so here also when you write the algorithm, it would be much convenient if you add the result of the first with the second. Okay, then this result, whatever the result you got, that can be added with this, that can be added with this, like that it can be done. Okay, initially how here we assumed for adding n natural numbers, initially we assumed s equal to 0. So initially we can, so these are the partial sum, this is one partial sum, this is one partial so sorry. Okay, see this is this is the partial sum at the first level. Okay, at the second level what will be the partial sum? Here we are not calculating, but if you calculate at the second level, it will be this 1, 0 plus 1 is 1, 1 plus 0 is 1, 1 plus 1 is 1, 0, carry 1. Okay, so 1 plus 0 is 1, that is that carry. Okay, so this is the partial sum. So this partial sum at every level you can calculate. Okay, initially we can assume partial sum as 0. Initially we can assume partial sum as all zeros. Then at this stage partial sum will be 0 plus 1 1, 0 plus 0 0, 0 plus 1 1, 0 plus 1 1, like that every time we can add the partial sum. Okay, so along with this we should also consider that. Okay, so instead of you can alternatively we added the partial products at the end. Alternatively alternative would be to add the partial products at each stage. Okay, right. So these are the rules to implement multiplication. Okay, if the ith bit of the multiplier is 1, so this is the multiplier, right? This is the multiplier. If the ith bit of the multiplier is 1, shift the multiplicand by I times and add the shifted multiplicand to the current value of the partial product. Okay, if the ith bit of the multiplier is 1, shift the multiplicand by I times and add the shifted multiplicand to the current value of the partial product, and hand over the partial product to the next stage or the next level. Okay, the value of the partial product at the starting stage would be 0. Initially we will assume the partial product value as zeros. Okay, so this is the intuition. This is what this would be the intuition, like how you can make a computer to multiply, right? Okay, so multiplier is nothing but what it is a, so we have understood that multiplication is nothing but it is a repeated addition with shifting of the multiplicand. So how it can be implemented? So basically it can be implemented by using full adders. So full adder is a circuit. A full adder is a circuit which is used to add n bit numbers. Okay, that much you understand. So full adder is a circuit which is used to add two n bit numbers. Okay, So there is a full adder which will add two n-bit numbers. Okay. This full adder takes two inputs. What are they? One is the previous partial product. Okay. If this is the first time, if this is the, so in the original, if you are encountering the zeroth bit of the multiplier also, then also you will have the partial product, because initially we assume the partial product is 0. So there will be some partial product. Okay. So there are two inputs for the full adder. The first input is the incoming partial product. We call it as PPI. Okay. So PPI. Okay. That the partial product in the ith stage. Okay. So here if you see this, you can call it as PP0. PP0. Okay. After adding this and this, you will get a partial product, right? So that is same 1101. That you can call it as PP1. That you can call it as PP1. Okay. Partial product 1. Okay. Similarly, after adding this with this, you will get a partial product, right? So this is 1, this is 1, this is 1, 1 plus 1 0, carry 1, 1 plus 1 0, 1. So this will be called as partial product 2. This will be called as partial product 2. Okay, right? So there is another one here. Okay, this will be called as partial product 2. And then when you add these zeros, again you will get the same thing. Basically it is what, 110. So that will be called as partial product 3. Okay. So like that, what I am trying to say in the sense, you will get partial product at every stage. Okay. So that partial product is one of the input for the full adder. Another input is what? Another input is the result of an AND gate. Another input is the result of the output of an AND gate. And this AND gate, it takes two inputs. This AND gate, it takes two input. What are the inputs it takes? It takes one input is the ith bit of the multiplier. Okay, one input is the ith bit of the multiplier, and another input is the jth bit of the multiplicand. Another input is the jth bit of the multiplicand. Okay. So because what should we do? And see, if you see and what it will do, if it is both are 1, it will result in 1. Okay, both are 1, it will result in 1. If both the inputs are 1, the output will be 1, otherwise the output will be 0. Okay, 1 0, it will be 0. Or 0 1, it will be 0. 0 0 also it will be 0. Okay. So from this what you can infer, AND gate is similar to multiplication. AND gate is similar to multiplication. 1 into 1 is 1. 1 into 0 is also 1 into 0 is 0. 0 into 1 is 0. 0 into 0 is 0. So why here we are using AND gate means AND gate is equal to multiplication. Okay, because every bit of the particular bit of the particular bit of multiplier should be multiplied with every bit of the multiplicand. Okay, so 1 into 1 you got this 1, 1 into 0 you got this 0, 1 into 1 you got this 1. So that part is done by this AND gate. Okay, so you can see this ith bit of multiplier, for ith bit of multiplier you will do this for depending on the number of bits. Okay, this will not be done one time. Okay, for here 4 times. In our case there is 4 bits. Okay, here in our case there is 4 bits. So this will be something like a loop. This will be something like a loop which will be repeated for j is equal to 0, j is equal to 0 to j less than or equal to 3. Okay, to j less than or equal to 3. Okay, so 0th jth bit will be performed AND with the ith what you call 0th jth bit will be performed AND with ith multiplier bit. What is that value? Take that. Okay, okay, let us assume x naught. Okay, then first jth bit, first bit of the multiplicand with the ith bit of the multiply, perform AND, the result is x1. Okay, then second bit of the multiplier with the ith bit of the second bit of the multiplicand with the ith bit of the multiplier, perform AND, what is the result? X2. Okay, then third bit of the multiplicand with the ith bit of the multiplier, what is the result? X3. Okay, so now you got the 4-bit input. Okay, so this 4-bit input will be performed and will be added with, using a full adder, it will be added with the partial product. Okay, so this is how, and then you and then you will get the partial product for the next stage, and then you will get the partial product for the next stage. This may also lead to carry. Now this I will be incremented. Okay, again this will become I is equal to I plus 1. Okay, so it is something like two loops, one outer loop and one inner loop. Okay, the outer loop also will repeat for 4 times, and for each iteration of outer loop the inner loop will repeat for 4 times. So I you can consider as an outer loop. Okay, for every iteration of this outer loop, this J loop will repeat for 4 times. Okay, so this is, so if you want to implement as an algorithm, this is how it should be done, right? Okay, this is the basic understanding, like how multiplication will be done by a computer. Fine. Okay, so if you see the hardware part, there is something called as a combinatorial array multiplier. Okay, this is one way of implementing multiplication. It can be done by one type of multiplier which is called as combinatorial array multiplier. Okay, so basically it uses for example, to multiply a 4-bit multiplicand with a 4-bit multiplier, to multiply a 4-bit multiplicand with a 4-bit multiplier, it has to use 16 full adders. It has to use 16 full adders. Here you can see all these are full adders. Each and everything, this is one full adder, this is another full adder, this is another full adder. All these are full adders. So this circuit basically it shows like how a 4-bit multiplicand will be multiplied with a 4-bit multiplier, right? So you can see this is multiplicand. Initially the multiplicand is given as input, okay, for each of this. Okay, and from here the multiplier is fetched. Okay, from here the multiplier is fetched. Okay, and initially we are assuming the, what you call, the partial product will be 0. Okay, so these zeros represents partial product. Initially there is no partial product, all partial products were 0. Okay, so this is why, so that it is 0. Okay, and then every bit. Okay, so first time this it will do only with the 0th bit of multiplier. Okay, the 0th bit of multiplier. So you know the input of what you call, the input for full adder is what? The input for full adder is, it is the partial product and the output from the AND gate. Okay, so this Q0 will go to the AND gate. This Q0 will go to the AND gate, and that will be multiplied with M0, and the result will be, and whatever the result, that will be added with the 0th, I mean the least significant bit of the partial product. Okay, so now you got one value. Similarly, again Q0 will be multiplied with M1, and that result will be added with the next bit of the partial product. Okay, and then Q0 will be multiplied with M2, that will be added with the next bit of the partial product, and then Q0 will be added with M3, and that will be added with the next bit of the partial product. So now once this is done, you get one set of partial products. Okay, that is the first level of partial product, right? First level of partial product. Then Q1 will be multiplied with M0. Okay, Q1 will be multiplied with M0, and that will be added with the previous partial product. There is one shifting is done here. Okay, there is no full adder here. Okay, in this level there is no full adder, so it is added with the partial product of the whatever the which bit of the partial product. The first bit of the partial product is added with the whatever the result of the AND from Q1 and M1 you are getting. Okay, sorry, not Q1 and M1, Q1 and M0. Okay, it's M0, Q1 and M0. that result, q1 and m naught, that result will be added with the first bit of the partial product, previous partial product. Okay, q1 and m1, that result will be added with the second bit of the partial product. Okay, q1 and m2, that will be added with the third bit of the partial product. Okay, q1 and m3, that will be q1 and m3, that will be added with the uh, lost q1 and m3, uh, that will be added with I mean, so q1 and m naught is added with the first bit, q1 and m2, that's added with the second bit, q1 and m2, that's added with the third bit. Okay, q1 and m4. Okay, so that will be added uh, with, if there is any carry, it will be added. Okay, in the previous partial product, if there is a carry, it will be added, otherwise the carry will be assumed as 0. With that, it will be added. Okay, like that this circuit works. Okay, so I guess you are following here. Everything is a full adder. It means it takes one bit from the respective partial product, and one bit is calculated by performing AND between the respective q naught and the respective q and the respective m. Okay, so this entire thing is with q naught, multiply q naught is multiplied with m naught, q naught m1, q naught m2, q naught m3. This is q1. q1 means, q naught means 0th bit of multiplier, q1 means first bit of multiplier, this is q2, second bit of multiplier. Okay, with m naught, m1, m2, m3. Okay, m naught, m1, m is multiplicand, this is q3, right? And finally you get the partial product. Okay, so this is how the circuit is implemented, right? But you can see here, actually this is for a 4-bit number, but in a typical computer, if you see, the number will be either 32-bit. So when you perform 32-bit multiplication, you can see how many full adders you have to use. You have to use 32 into 32 full adders. That means, and also it will create lot of delays. Okay, so depending on the, see, the values has to propagate from one full adder to another full adder, which will create huge delays. Okay, so this may not be the efficient technique. So we should think of, is there any way to improve this? Okay, so this circuit, whatever the combinatorial array multipliers which we have discussed, this is extremely inefficient. Okay, it has a high gate count for multiplying numbers of practically numbers like 32-bit or 64-bit numbers. Okay, the delay will be high. Okay, so so we have to improve the gate efficiency by using some techniques. So we'll be using not only combinatorial techniques, but we'll be using some sequential techniques also in order to improve the performance. Okay, so next we'll be discussing a sequential technique to improve the performance. Okay, right? So in this technique, what we are going to do is, in the previous from the previous technique, we are going to infer some wisdom. Okay, it's really a wisdom. You can see here. So recall the rule for generating the partial products. What is the rule for generating partial product? From the previous understanding, if the ith bit of the multiplier is 1, then shift the multiplicand by I times, shift the multiplicand to the left, to the left by I times, and add it with the partial product, This is the rule. Based on this rule only, the combinatorial circuit works. Okay, what is the rule? If the ith bit of the multiplier is 1, then left shift the multiplicand by I times and add it with the partial product. If the ith bit of the multiplier is 0, okay, then in all the bit position fill up with zeros and left shift by I times and add it with the partial product. Okay, so here multiplicand has been shifted left, but and it is added with the partial product. We are not shifting the partial product. Okay, in combinatorial circuit. Okay, but in sequential circuit, we are going to do the reverse. Okay, so shifting the multiplicand left by I times and adding it with the partial product is equivalent to, please understand carefully, shifting the multiplicand to the left by I times and adding with the partial product is equivalent to shifting the partial product to the right, shifting the partial product to the right for I times and adding it with the multiplicand, unshifted multiplicand. Okay, in combinatorial circuit what we did, we shifted the multiplicand to the left by I times and added with the partial product. Okay, in sequential circuit what we are going to do in the sense, right shift the partial product by I times, right shift the partial product by I times and add it with the unshifted multiplicand. Okay, this is the rule we are just going to reverse the rule. Okay, so adding a left shifted multiplicand to an unshifted partial product is equivalent to adding an unshifted multiplicand to a right shifted partial product. Okay, so this is the basic rule by which the sequential multiplication algorithm is going to work. Okay, so here the right shifted partial product will be added with the unshifted multiplicand. Okay, so let us see how it works.